Okay, hello Extension 1. Welcome back to Term 2. It's lovely to see you guys back at school again, although not physically. What I'm going to do is I'm going to continue looking at continue this topic that we've been looking at for the last while. We've been looking at kind of more in-depth look at functions. In advanced, we've been looking at a bit of function stuff. What we're doing in Extension 1 is now we're looking at a few further things to do with functions. In particular, we're looking at graphing a few more difficult to graph functions. And so that's what this first topic of this term is going to look at. This first section, what we're going to do is look at graphing polynomials. Now, in advance, we're going to actually look at one particular method of graphing polynomials. So please stay tuned if I haven't already looked at it, looking at how we graph polynomials in advanced. This is just a few more additional things that build off of those methods in advanced. I'm not actually going to cover the stuff that we cover in advanced. You can have a look at that when we do it with the advanced class. But what I'm going to do is I'm going to do a bit of a quick recap at the start here, just on polynomials. Now, if you recall, polynomials are a group of functions that look like this. They've got, so for example, if you have a look on the screen now, I've got p of x is equal to an x to the power n plus an minus 1, x to the power n minus 1, and so on until we get a constant term at the end, a0. Now, the thing that we noticed was that these are all this is all made up of multiples of positive integer or whole number powers of x. So if you look at this polynomial, we've got x terms and the powers are all positive integer values. So you can't have negative numbers and you can't have fractions in there. Now, we also looked at, in Extension 1, we looked at factor theorem. And factor theorem told us that we can actually factorize a polynomial. So polynomial p of x can be factorized. We can do it a few times, but we can write it as x minus alpha times q of x if p of alpha is equal to 0. So if we sub in a number into a polynomial and it gives us a 0 value, we know that we can factorize out x minus alpha. If you remember, so x minus alpha divides p of x if and only if p of alpha is equal to 0. That's what we looked at when we looked at factor theorem. We're actually going to build off of these ideas and actually use that to help us figure out how to graph, or what a polynomial looks like when we graph it on a Cartesian plane. So here we're going to actually look at a few different things and focus on a few things that we don't actually get to cover in advance. So here, let's have a look at this first part. Now, there should be a booklet that I've uploaded online. If I haven't, please let me know. Or it's coming out to you if you've requested for a physical copy. This is in your booklet. This is just a quick kind of like checkbox. Now, this first box looks at the behavior of polynomials for large x. And so what we need to do is actually need to look at, it uses this notation here that you see over here, where you've got x arrow infinity. What this arrow tells me is, it's in words, it means as, oh, actually, let's break this whole thing down. This whole thing here actually says, as x approaches infinity. As x approaches infinity. So as x approaches infinity, or as x goes to infinity, what it's describing is basically what happens to your polynomial as x becomes really, really, really big, like a really, really big number. On your Cartesian plane, if you have a look at your Cartesian plane, this is the same as going, well, what happens when we move further and further to the right of the graph? Because when you go to the right of the graph, and I need to make sure I've got this clear. When you go to the right of the graph, the x values get bigger and bigger and bigger, right? You start off with like 1 over here, and then as you get further and further to the right, you go to like 100, then you go to 1,000, and so on. So what we're looking at here is basically what happens to the graph when we move further and further to the right. What happens to the graph when we move further and further to the right? And in the same way, if we have x goes to negative infinity, that's what happens when we go to the other side of the graph. We go towards the left. So this is as x goes to negative infinity. Because when you go to negative infinity, negative 1, that's a small number. But then you go to negative 10, that's an even smaller number. And as you keep going further left, that's what happens when x approaches those values. So so when you see this notation, x right arrow infinity, it means that as x goes towards infinity, and the other notation is as x goes to negative infinity. Okay, so what happens here? Let's read through this box. So suppose that p of x is a polynomial of degree at least 1 with leading term a n x to the power n. So that's what we had when we looked at polynomial notation. Now this first dot point, as x goes to infinity, p of x goes to infinity if a n is positive, and p of x goes to negative infinity if a n is negative. So let's actually break this down and have a look at what this looks like visually. Now I'm going to move all of this to the side so I can actually get a bit more space to work with. Oop, that didn't work out. That's okay. Okay, I'm going to move this to the side for a second. Now, let's look at this first dot point. Now, there's two conditions that we're looking at. If a n is positive, and if a n is negative. Now, a n, if you remember, a n is just your leading coefficient. So the leading coefficient, if it's positive, let's see what happens. P of x goes to infinity. Now, p of x is just your polynomial. P of x is another way of thinking of the y value. Now, if we have a look at our Cartesian plane, if y goes to infinity, which way are we going? That means we're going up. So here, if we're going up, that means y goes to infinity. And the other way, direction, that's y goes to negative infinity. It's getting a bit messy here, but I'll show you in a second. So if a n is positive, that means as x goes to infinity, p of x goes to infinity. So it gets bigger and bigger and bigger. So what it looks like is, let me draw this. If I've got my Cartesian plane, as x goes to infinity, p of x, our polynomial, also goes to infinity if the leading coefficient is positive. So also goes to infinity. So infinity is going upwards, negative infinity is going downwards. So p of x goes to infinity. So what that would look like for your graph is it looks something like this. On the right-hand side, it goes towards this top right-hand corner. So if our leading coefficient is positive, it goes towards that top right-hand corner. However, if an is negative or less than 0, let's do the same thing. If as x goes to infinity, p of x, so this is x goes to infinity, p of x goes to negative infinity. So it goes the other direction, actually goes down this way. P of x goes towards negative infinity. So that leading coefficient tells me where does my polynomial end up if I'm going towards the right. So if I go towards the right, where does my polynomial end up? And so here, let me just draw it out. So what it'll look like is something like this. So you might end up having, polynomials can look like that. It goes down towards the bottom right-hand corner. Okay, so that's what this first dot point tells me. The leading coefficient tells me if it goes towards as x goes to infinity, so as x gets really, really, really big, does it go towards the top right-hand corner? So does p of x get bigger? So that's if it's greater than 0. Or does it get smaller and go towards negative infinity? So that's what this leading coefficient tells me. Now let's have a look at the second dot point. The second dot point tells me is x goes to negative infinity, so the other direction, so when x goes towards the left, what happens? So p of x behaves the same as x goes to infinity if the degree is even, but p of x behaves in the opposite way if the degree is odd. So here, the second thing we need to look at is actually the degree of the polynomial. So if you remember, the degree is just the highest power of your polynomial. So what this actually tells us is that if the degree of the polynomial is even, and the other one is degree of the polynomial is odd, what happens? Well, if you read here, if the degree of the polynomial is even, then p of x behaves the same way as when x goes to infinity. So let me draw this out. I'm going to draw two examples. So if p of x is even, as x goes to infinity, if the polynomial is going towards positive infinity, so if so we have as x goes to infinity, if p of x goes towards infinity as well, then if it's even, it matches it as well when x goes to negative infinity. So as x goes to negative infinity, for this blue one, p of x goes to infinity as well. So it matches that shape. So for example, you could have a polynomial that looks like this. And so here we notice that both the sides match up. So this is if it's even. The other case is that if it goes the other way, if p of x goes towards negative infinity when x goes to infinity, so this is x goes to infinity, p of x goes to negative infinity, well, on the other side, we're going to have the same thing. So we're going to have, when x goes to negative infinity, p of x is also going to go to negative infinity. So here, these two match up. I actually didn't write it for the first one, but let's actually write it out. So x goes to infinity, p of x goes to infinity. And so these two match up. So for example, you could have something that goes like this. And so if you notice on both ends, they both go the same direction. So the degree tells me where does the starting side, so the left-hand side, where does it go to? Does it match what the right-hand side does? Does the left-hand side match with what happens on the right-hand side? Now, if it's odd, it's the opposite of that. Instead of matching, it actually goes in opposite directions. So let me do a couple examples of this. So let me draw it a little bit better. Actually, it should be more center on x and y. If the degree of the polynomial is odd, what this tells me is if, for example, on one of my polynomials, I have, let me do it in orange, x goes to infinity, p of x goes to infinity as well. Well, for that polynomial, if it's odd degree, then that means that x goes to negative infinity. For the other side, so if x goes to infinity, instead of p of x going to infinity like we have over here, let me write it here, p of x will actually go to negative infinity. So for example, let me draw this orange one. So if it goes towards infinity on this side, and it's odd, they're going to go in opposite directions. So here, I'm going to have these two go in opposite directions. So if its degree is odd, it goes in opposite directions. If the degree is even, it goes in the same direction. Okay, so that's what this bit is talking about. So the behavior for large values of x. As x goes to infinity, what happens? You have to look at the leading coefficient. Then if you're looking for, and when x goes to negative infinity, well, then you look at the degree. So here, this is for x goes to infinity. We look at the leading coefficient. For x goes to negative infinity, we look at the degree, and then we have a look at what happens in the first step. So that's what we do when we're looking at the behavior of polynomials for big values of x.